Hey everyone, and welcome to this explainer. Today, we're diving deep into the fascinating geometry of triangles, but we're going to do it by learning how to think like true math investigators. You know how your eyes can play tricks on you in the real world, right? Like with crazy optical illusions, weird camera perspectives, or misleading shadows? Well, geometry is basically the ultimate lie detector test. In 8th grade math and beyond, being an investigator means prioritizing solid, indisputable evidence over those misleading visual appearances. So we're not just going to trust our eyes today, we are trusting the facts. Together, we're going to build a rock-solid understanding of how triangles actually work, from the inside out.
Okay, let's take a quick look at our agenda. We'll start by distinguishing hard geometric evidence from mere appearance. Then we'll explore congruence criteria, investigate some really cool special segments hidden inside triangles, use proportions for indirect measurement, and finish up with a concise recap and a transfer challenge.
All right, Section 1, Appearance versus Geometric Evidence. Let's establish the absolute cardinal rule of geometry.
In geometry, you simply cannot trust a quick glance. You have to rely entirely on defining attributes as your core evidence. We're talking about undeniable facts here. Things like the exact number of sides, verifying the presence of parallel lines, or a specifically given angle measure. You've got to train your brain to totally ignore the non-defining stuff. It really doesn't matter what color a shape is, how it's tilted on the page, or if it's a super sloppy sketch. Actually, sometimes a textbook drawing is intentionally drawn out of proportion just to try and trick you. A badly drawn angle that looks sharp might actually be a perfect right angle if the math symbols explicitly state that it is. The facts are your only evidence. And what's really fascinating here is that we don't even need a picture to build a perfect shape in our minds. Look at these bullets. You don't see a picture of a triangle at all, do you? Instead, you have to rely entirely on these properties as your exact geometric evidence. We know we have a closed shape with 3 vertices, we know 2 side segments are exactly 5 units long, and we know the included angle, the one wedged right between them, is exactly 45 degrees. By stripping away the visual entirely, we're forced to rely on absolute mathematical reasoning. It's kind of like the ultimate blindfold test for a math investigator.
Moving on to Section 2, Congruence Criteria and Reasoning. Let's see how this exact evidence helps us prove that 2 triangles are perfectly identical.
So, based on 8th grade and high school geometry standards, we use definitive criteria to prove shapes are congruent. And congruence just means they are absolutely identical, the exact same size and the exact same shape. We use criteria like ASA, angle side angle, SAS, side angle side, and SSS, side side side, as a rock-solid evidence. These are derived from rigid motions. Think of a rigid motion like sliding, turning, or flipping a perfectly carved wooden puzzle piece across a table. The piece never bends, it doesn't stretch, and it never shrinks. These criteria let us mathematically guarantee that 2 triangles are that exact same puzzle piece, without ever having to physically cut them out and overlap them to check.
Okay, it is time for our first pause check. Put on your math investigator hat and think back to the clues we just established. If you have 2 completely separate triangles, but they both have a side of exactly 5 units, an included angle of exactly 45 degrees, and another side of exactly 5 units, does this specific combination guarantee congruence? Go ahead and pause this explainer right now to think it over. If you said yes, you nailed it. The immediate reasoning behind this is that because both triangles share a side, an included angle, and another side of equal measure, the side angle side, or SAS, criterion steps in to guarantee their congruence. It's super satisfying because this provides completely valid, airtight reasoning. We just proved the absolute truth about these 2 shapes without even needing to see a physical drawing of them. All right, let's slide right into Section 3, Special Segments Inside Triangles. We are shifting our focus to the internal organizational framework of the shape. By following these exact deliberate steps, we uncover the hidden architecture inside the triangle. First, imagine drawing a median. You start at a corner, the vertex, and draw a straight line directly to the exact middle of the opposite side. If you do this for all 3 vertices, something amazing happens. They all intersect at a single, perfectly balanced point. Literally, if you cut the triangle out of cardboard, you could balance it perfectly on a pencil tip right at that intersection. Then we have the mid-segment. If you connect the midpoints of any 2 sides, you create this special line. Geometric theorems prove that this mid-segment is always perfectly parallel to the 3rd side at the bottom, and it's exactly half of its length. These special segments organize the inside of a triangle with just incredible precision.
Now let's head into section 4, proportions and indirect measurement. We're looking completely outward now at how we measure the truly unmeasurable in our world. So, while congruence means two triangles are identical puzzle pieces, similarity means they are the exact same shape, just different sizes. Think of it like a mini-me and a mega-me. The angle-angle similarity criterion tells us that if two triangles simply share the same internal angle measures, their corresponding side lengths will always maintain a strict proportional relationship. This is a massive tool for mathematicians. Think about it. How do we know how tall a skyscraper is without dropping a giant tape measure from the roof? We use similar triangles. By matching the angles, we can perfectly scale up the proportional sides to calculate distances we could never easily reach on our own.
Which brings us to pause check number 2. Let's solve a real-world problem. We have a flagpole casting a shadow that is exactly 10 feet long. Nearby, standing in the same sunlight, a 5-foot-tall student casts a 2.5-foot shadow. Please pause the explainer right now, grab some scratch paper, and use the concept of similar triangles to figure out the exact height of the flagpole.
Let's walk through the immediate reasoning here. It is all about proportionality. The student and their shadow create a right triangle, and the flagpole and its shadow create a larger, similar right triangle because the sun's rays hit them at the exact same angle. Just look at the beautiful, simple math of the smaller triangle. The student is exactly twice as tall as their shadow, right? Since 5 is double 2.5. Therefore, the flagpole must also be exactly twice the length of its 10-foot shadow. Double 10 is 20, meaning the flagpole is exactly 20 feet tall. Finding that height so easily brilliantly illustrates the real-world power of geometry, which leads us nicely into section 5, recap and transfer question.
To concisely recap today's investigation, let's open up your brand new toolkit. First, you must always differentiate hard geometric evidence from misleading visual appearances. Second, you can totally rely on rigid criteria like SAS for valid reasoning to prove congruence without even needing a picture. Third, remember that special segments, like medians and midsegments, logically organize a triangle's internal structure. And finally, you can confidently apply proportional relationships to brilliantly solve complex indirect measurements.
I am going to leave you with this final transfer question to investigate entirely on your own. Think about proportions in architecture. If you're designing a wheelchair ramp that requires a specific slope, and you geometrically increase the run, which is the horizontal base along the ground, how must the vertical rise adapt to maintain that exact same proportional, safe slope? Use the rules of similar triangles we explored today to figure it out. Because geometry isn't just a bunch of rules on paper. It actively dictates the physical world we walk, drive, and roll on every single day. Thanks so much for joining me in this explainer, and keep thinking like a math investigator.